Hi everyone, this is Dr. Rich and I'd like to review the electrocardiogram with you. So this first slide shows the electrocardiogram, which we affectionately refer to as the ECG. The ECG is recorded with electrodes at the surface of the skin, and we really need to pay attention to units. So I want to first describe the axis labels for a standard electrocardiogram. You won't always see these labels, but I think it will really help you to understand what's going on. So if we first look at the horizontal axis, we can see that one cardiac cycle takes about 0.8 seconds or 800 milliseconds. And what I've labeled here with this horizontal line is the time from one atrial systole, or this small bump, to the next atrial systole, or this small bump. And we'll review that in just a minute. The next thing we need to look at is the vertical axis, and what I've got labeled here is 1 millivolt. So you can see that the height of an electrocardiogram is 1 or 2 millivolts. I want you to think about a cardiac myocyte and a cardiac action potential, and what you've learned is that in a cardiac action potential, the resting membrane of that cardiac myocyte goes from roughly minus 90 millivolts all the way up to plus 30 millivolts. What that means is this 120 millivolt change from minus 90, the depolarization, all the way to plus 30, really can be measured at the surface of the body, not in the heart, but at the surface of the body, and by then that signal decays, so it's only about a millivolt in magnitude. So let's move on, and let's learn what these individual bumps are, and what's slowly writing out here is the P, the QRS, and the T wave. One cardiac cycle goes from P wave to P wave. Again, it's about 800 milliseconds at rest. The P wave is atrial depolarization. The QRS wave is ventricular depolarization. The T wave is ventricular repolarization. So remember, depolarization means we go from minus 90 millivolts, more positive, whereas repolarization means we're going back to rest. So it means we're returning to minus 90 millivolts, and hopefully you'll remember that what the electrocardiogram results from is the electrical activity in a cardiac myocyte. So those muscle cells are going from minus 90 to plus 30 millivolts. Well, when we go from minus 90 to plus 30, that's depolarization. That means we're getting closer to zero. Repolarization means we're going back down to minus 90, and you go to minus 90 from that plateau phase, that really elongated portion of the cardiac action potential where calcium is entering the cardiac myocyte through voltage-gated calcium channels, and that calcium really contributes to ventricular contraction. Now I want you to keep the electrical activity separate from the function of the heart or the contraction. The electrocardiogram refers to the electrical activity. That's what it measures. But we can infer what's happening functionally, and I have that labeled in this panel. So we've got atrial depolarization, and we've got ventricular depolarization in this electrocardiogram. And what I'd like to do now is to show you, using a red highlighter, where we have atrial depolarization. There it is, and there's ventricular depolarization. Now, the ventricular depolarization takes longer because there's more mass of the cardiac myocytes than the atrial myocytes. The peak is also bigger because the ventricles are so big. And what you can know from an electrocardiogram is really the size of the tissue that's depolarizing. Now, how do we get back to rest after this long depolarization? And here we have the ventricular repolarization. This is the T wave, and I've got it labeled in green. So you can see with this green highlighter, we have the ventricles going back down to minus 90 millivolts. Again, the green is ventricular repolarization, so that's going from the plateau phase back to minus 90. The red is atrial depolarization or it's ventricular depolarization. And again, that results from a cardiac myocyte firing an action potential. And this goes on and on and on throughout life. Now I told you we'd get to function, and here we are. Systole and diastole. You all know these words, and what you should know is systole refers to contraction of cardiac myocytes. Diastole refers to relaxation. Now remember, contraction happens when calcium enters a cardiac myocyte. That occurs during the plateau phase of a cardiac action potential, which is a little bit after that action potential fires, which means that there's some difference between the timing of contraction and the action potentials or the electrical activity. So here in red, I've shown where atrial systole occurs, really close to the P wave, right? When the atria are depolarizing. Here's ventricular systole. And again, this happens when those cardiac myocytes fire action potentials, but it starts a little bit into the QRS phase. Now I can show you atrial diastole, or when the atria are relaxed, which is quite a long time, right, during a cardiac cycle. And here's when the ventricles are relaxed, or ventricular diastole. This is, if you can remember, when the ventricles are filling. Okay, so we've gone over the electrocardiogram, which measures the electrical activity of the heart using electrodes placed at the surface of the skin. I hope this helps, and good luck on your test and later in your lab. Bye now.